Hello everyone, today we're gonna learn about impulse and momentum.
In chemistry, we learn about the conservations of matter. Here in physics, we learn about the conservations of energy. This concept can be extended to formulate another law, and that is the law of conservations of momentum. Momentum is a term we may be familiar with, but once again, we must learn the rigorous definitions of this word. And linear momentum is defined as mass times velocity, which will be represented by the letter P. Momentum is a vector quantity as it involves a velocity vector by multiplied by the scalar value of the object mass. This means momentum will be expressed with SI units of kilogram meters per second. In this case, our everyday use of the word is fairly accurate. And we might say that as balls rolls downhill, it will gather momentum. This is true because velocity of ball will increase as the force of gravity accelerates towards the ground. The more momentum the ball gathers, the more difficult it will be to bring it to a stop. And an object in motion can therefore have a larger momentum by virtue of being more massive, like a huge boulder, or also by moving at high velocity like a tiny hailstone or meteorite falling from the sky. If we consider a car in motion, it too will have a momentum equal to mass times velocity. And if you slam on the brakes to avoid collisions, the car will skid a certain distance because force must be applied over some durations of time to bring a moving object to rest. The heavier the car and the faster it was moving, the greater this factor will be. A small force acting over a long time will do it, like if you take a foot off the gas and let the frictions from the road slowly stop the car, or a large force acting over a short time could do it, like firmly applying the brakes to the tires. The force that it applied multiplied durations of time that it is applied is called the impulse, which will be measured in Newton seconds. The relationship between impulse and momentum is summarized in the impulse-momentum theorem. It states that the impulse F delta t is equal to the change in momentum, or delta p, which can be expressed as mv final minus mv initial. So, if you apply some force to push an object for some durations of time, that object will gain a proportional amount of momentum. If an object loses momentum, it must be imparting some force to something else over some time period, just as the word energy theorem describes conservations of mechanical energy. The impulse-momentum theorem describes conservations of linear momentum. Another ramification of this theorem is that the force imparted on a moving object when it strikes some surface will be very large if the impact is initious and much less if the impact involves some time durations. If you fall off your roof onto the ground, it will hurt, but if you fall onto a trampoline, it won't be as bad because the change in momentum imparted on your body, instead of happening instantly, will be delivered over the entire durations of your contact with the trampoline surface as it stretches from the force of your fall. This is also why baseball players are taught to swing through the ball rather than stopping the swing upon impact, because if contact is maintained between the bat and the ball for as long as possible, the maximum possible force will be imparted upon the ball. In the case of an object striking another object, total momentum will be conserved through the collisions, and the sum of the momenta of the two objects will be the same before and after the collisions. The easiest example of this concept involves balls on a pool table. We will often observe that one ball has momentum while the other does not, and after the collision, the first ball has stopped and all of its momentum has been imparted onto the other ball. This type of scenario illustrates conservations of momentum. There is much more to discuss regarding collisions, which we will go over in the next, but first let's set comprehensions.
Okay, let's learn about linear momentum.
First things first, what is linear momentum? Linear momentum is defined as mass and velocity, where the SI unit is kilogram meter per second or Newton. For the equation for the linear momentum, we have P is equal to mv, where P is momentum, m is mass, and v is velocity.
I am so sorry, I meant to say Joule, but I accidentally say Newton. The real unit is Joule.
For the example, let's say we have a 4 kg box moving with 2 meter per second velocity. What is the momentum? So let's use the equation, which is P equal to mv. So the momentum is equal to 4 kg times 2 meter per second. So we get 8 kg meter per second, or you can use Newton. So the momentum is 8 kg meter per second.
I am so sorry for this one too. I meant to say Joule, but I accidentally write Newton there.
The law of conservation of momentum. This is mean the momentum is conserved, which means the total momentum before collision and after collision will remain the same. So we have the formula m1u1 plus m2v2 equal to m1v1 plus m2v2, which we have m is the mass, u is the initial velocity, and v is the final velocity.
Next, let's talk about elastic and inelastic collision. For the elastic collision, the object moves to the opposite direction after the collision. And the momentum before and after collision is same because momentum is conserved. The total kinetic energy is also conserved. So the kinetic energy before and after collision is same. So total kinetic energy is initial is equal to total kinetic energy final, as we can look at the equation below.
Next is inelastic collision. Inelastic collision is when the objects stick together after the collision. The momentum before and after collision is same, which is the momentum is conserved, same like the elastic collision. But the total kinetic energy is not conserved, which means there is an energy loss during the collision. We can find the total kinetic energy initial equal to total kinetic energy final plus energy loss. For the difference between elastic collision and inelastic collision is the elastic collision, the kinetic energy is conserved, which means there is no energy loss during the elastic collision. But for the inelastic collision, there is a kinetic energy loss. So the total kinetic energy is not conserved. And for the inelastic collision and elastic collision, both of the momentum is conserved. But for the inelastic collision, we can use m1 plus m2v because after the collision, the object move together as one body, meaning that we can just simply add the two masses together. Example, let's say we have two identical balls hit each other with velocity 0.51 meter per second and 0.25 meter per second. What is the final velocity if the collision is perfectly elastic? Now, we know that during elastic collision, there is no kinetic energy loss. So we can assume that the velocity before and after the collision is same. So the collision is V1 is equal to 0.51 meter per second and V2 is 0.251 meter per second, but with negative because it moves to the opposite direction. So the second velocity for the second ball is negative 0.25 meter per second. Example, let's say we have a 20 kg toy car traveling at 6 meter per second, hit a stationary 10 kg toy car locking the two vehicles together. Find the final velocity of the two cars. M1 we have 20 kg, M2 we have 10 kg, and initial velocity 1 we have 6 meter per second, and the second initial velocity is 0 meter per second because it is at rest. Find V. So let's put all the variables we have in the equation and find V. And calculate, and we get V is equal to 4 meter per second. And calculate the energy loss. For the energy loss, we can simply just put all the variables we have with the velocity that we find in earlier in the equation and got around 120 joule of energy loss.